So let us begin with the last session of today in the morning. So today this will now be starting a new topic here, and we'll be talking about Hamiltonian graphs, right? So we yesterday when I introduced this notion that we said that does the graph have a special property? We said that the graph can be a tree, it can be a bipartite graph, and I said there may be several other properties. We are now going to study another property which is called as the Hamiltonian property, or a graph being Hamiltonian. So how many of you have heard this word Hamiltonian graphs? Okay, many of you have heard this, and so all of us understand what is a Hamiltonian graph, but I'll state it and define it clearly. So we have a graph G on n vertices, and we will talk about undirected graphs, and we will talk about simple graphs. So we will not have multi-edges and we will not have loops in them. So we'll always, in this lecture, we will talk about simple graphs. So a graph G is said to be Hamiltonian if it has a simple cycle which covers all the vertices of the graph, which is also called as a spanning cycle, right? So G is Hamiltonian if G admits a simple spanning cycle. So this automatically says that a spanning cycle, what do we understand by a spanning cycle? A cycle that goes covers all the vertices. It is simple, it goes over every vertex exactly once. It starts at some vertex and ends back at another vertex, right? So this is the definition of a graph being Hamiltonian. If it does not admit such a cycle, it is non-Hamiltonian, right? So we have this very simple task, that is, we would like to, given a graph in its adjacency matrix or adjacency list representation, again we will stick to adjacency list representation, we would like to answer this question: does this graph have a Hamiltonian cycle? That's the only question. So it's a decision question, it's not computing anything, it's a decision question. Does it have a Hamiltonian cycle? Maybe if it has, we may also want to output one, but before we go to that question, we will just ask, does it have one cycle? Okay, good. So just to make sure that we are on the same page, let me draw a few graphs and we will identify whether a graph, the graphs that we have drawn, which of them do have a Hamiltonian cycle. Yeah, so now the graphs are clear. Can you quickly tell me which graphs are Hamiltonian, which are not Hamiltonian? So minimum requirement is that every vertex should at least have degree 2, right? If you have a vertex which is a pendant vertex which has degree 1, you cannot hope to have a Hamiltonian cycle. So this is not Hamiltonian, is clear. Okay, what about G2? It has a Hamiltonian cycle. So if you want to say it has a Hamiltonian cycle, you show me a Hamiltonian cycle. Okay, A. So slightly louder. Okay, A, Y, D, B. X, A, Y, B, X, C, D, is this a it should end at A again, right? It's not a cycle. So this is not a Hamiltonian cycle. Yeah. Any other cycle that somebody can suggest? A X C D A X C D Y is it allowed? Okay, so this is not allowed. Two occurrences of X is not are not allowed, right? So this is not a Hamiltonian cycle. D C X B Y A this is not a Hamiltonian cycle, right? Okay, so if you wanted to argue that this graph does not have a Hamiltonian cycle, what could you possibly do? Yes? Huh? Sorry, louder. No. So we are not able to add edges to the graph. You see, so many of you have tried to identify an Hamiltonian cycle, but you have failed to do so. So maybe the answer is that there is no Hamiltonian cycle, maybe. Then if you have to convince me or convince yourself that there is no Hamiltonian cycle in the given graph, you cannot add edges to the graph, then how should you convince yourself? Okay, what are all possible ways of having a Hamiltonian cycle? Does it matter where you start? It doesn't matter, it's a cycle, so you start anywhere. So suppose anyway I'll decide that my cycle starts at A, it will also end at A. Then what are the possible things that I can do? I can try that I will go to X, or I can try that I can go to Y. These are the only choices that I have. So I can possibly try to explore all these paths, all these ways, and then see if one of them leads to a Hamiltonian cycle. Or in fact I can write down all the permutations on of n vertices and check. Some of the permutations are not valid. For example, if I write a permutation which is A, B and something else, then it is not a valid permutation, because anyway AB are not adjacent, so I cannot write that permutation. You cannot hope to have a cycle of that form. So I will discard permutations which are not valid permutations, and then there are permutations which are valid, but all of them should have something invalid, because otherwise if you have a valid permutation, then you will find that that is actually a Hamiltonian cycle, right? It doesn't matter where you start, because it will again loop back at the same vertex. But this way of convincing yourself or convincing me is very tedious. One is, on a large graph you have to try out all these permutations, right? So this is not an efficient way of convincing me. When I say you have to convince me efficiently, you have to give me a short proof, a succinct proof, that just like here you said that you cannot have a degree 1 vertex in the graph and then hope to have a Hamiltonian cycle, right? So now we are making a distinction between a short proof and a long proof, right? A short proof is a proof which, so at an intuitive level it can be described succinctly, but we will make it a little more formal in later stages, where it is polynomial in the size of the input, right, in some sense. Now, so this we will see later on, that in this class itself, that this graph does not admit a Hamiltonian cycle, and we will also see a small reasoning which will give us a short succinct proof of this fact. What about this graph, the graph G3? That is very simple. So A, C, E, D, B, A is a Hamiltonian cycle. Good. So now we see that there are graphs which do not admit a Hamiltonian cycle, but we do not know an easy way to convince ourselves, right? So what we are going to do is, we are going to look at two types of conditions. So the first condition is going to be a necessary condition. and the second condition is going to be a sufficient condition. So let us, before we look at the actual conditions, let us see what do we understand by a condition being necessary, right? So what do you think is a possible necessary condition for a graph to be Hamiltonian? So in particular, I am looking at, just like in the previous class in the morning, we said that we wanted some type of statement for the pre-visit number and the post-visit number, or we wanted to make a statement about a single strongly connected component and the pre-visit post-visit number. We wanted a relation of the form, if the vertex has this property in terms of the pre-visit number, post-visit number, then it belongs to a strongly connected component. And some of you also came up with the reverse conditions, that is, if it belongs to a strongly connected component, then it should have this condition. So let us try to understand which is necessary, which is sufficient. So in this context, let us try to understand this now. That is, when will you say that this condition is necessary? Any simple necessary condition? Degree of every vertex must be greater than 1, that is at least 2, right? So every vertex must have, so if G is Hamiltonian, that is if it admits a Hamiltonian cycle, then every vertex must have degree at least 2. This is a very simple and good necessary condition. It falls into the purview of being a necessary condition, right? So we first look at a necessary condition, which is a strengthening of this, right? And something that we possibly can intuitively also imagine about Hamiltonian graphs. So let us first ask ourselves, if the graph has to have a Hamiltonian cycle, then can you have a vertex which I will call it as a cut vertex? What is a cut vertex? A vertex which is whose removal disconnects the graph into 2 or more components, right? So let's say that there is this cut vertex. So just to make sure that this looks like a cut vertex, this is the way it looks like. So as soon as I delete this, I am going to split the graph into multiple components. Now can a Hamiltonian graph have such a cut vertex? No. So why? It won't be a, yeah, so any cycle that is a Hamiltonian cycle must visit this vertex, right? It must visit this vertex, it must visit, so let's say that it disconnects it into C1, C2, C3, any number of components, then the Hamiltonian cycle, once it enters C1, it must cover all the vertices inside the component C1, then it must visit the vertex V, but that should have been the end of the Hamiltonian cycle, right? And but this cannot be possibly true because you have a whole component C2 to visit and a component C3 to visit. So clearly if the graph is Hamiltonian, it cannot have a cut vertex, correct? So we will just go a little further. Everybody okay that it cannot have a cut vertex? Okay. So now let us look at what we saw yesterday, bipartite graphs. Yeah, so maybe before I go there, so is it clear? So what about a complete graph? Forget about other examples. What about a complete graph? Does it have a Hamiltonian cycle? In fact, it has multiple Hamiltonian cycles, right? And a complete graph is, I mean, so what we are seeing is trees do not have a Hamiltonian cycle, complete graphs do have Hamiltonian cycles. So if you have large number of edges, it seems good for the Hamiltonian cycle to exist. At the same time, having large numbers of edges is not necessary, because if you simply draw a big cycle and then add a very few number of edges, it still is going to be Hamiltonian, because the graph can be very sparse. It is just n-1 plus 1 and a few edges that you add here and there, so that it doesn't look only like a cycle. It still is a very sparse graph and it has a Hamiltonian cycle, right? So there can be extremes, but certainly if the graph is very dense, that is, it has large number of cycles, then we expect that maybe it will have a Hamiltonian cycle, and we want to formalize this. So now we know that a complete graph has has a Hamiltonian cycle. So let us now ask ourselves complete bipartite graphs. So this is we will call these as the A and B partitions. We know how to identify that whether it is a bipartite graph now. Now what do you mean by a complete bipartite graph? For every vertex on the A side you have edges to all the vertices on the B side. Similarly, every vertex on the B side has edges to all the vertices on the A side. This is a complete bipartite graph. So if so how many edges does this graph have? Cardinality of A into cardinality of B. These many edges are there. Now this is a relatively dense graph, right? Now what can we say about the graph being Hamiltonian or not? So let us try out a simple example. So maybe I will draw a graph with so this is my graph which has 2 vertices on the A side, 3 vertices on the B side, and I would like to see whether there is a Hamiltonian cycle. But remember, this is different from the Euler tour. The Euler tour of a graph is again a cycle which visits all the edges of the graph exactly once, and that condition what you are talking about is a necessary and sufficient condition for the graph being Eulerian. Okay, so now you have flipped the condition and you have said that it is a sufficient condition, which is okay, which is also a correct statement here. But what you want to say is that if a graph is Hamiltonian and it is complete bipartite, then cardinality of A should be equal to cardinality of B, right? In fact, what we are saying is if cardinality of A is not equal to cardinality of B, there cannot be a Hamiltonian cycle. And why would you think so? But in this example it's okay. I mean, why I mean, this example doesn't have a Hamiltonian cycle. Maybe you will do a brute force proof of this. But in any general, this statement is much more stronger. It is a general statement about complete bipartite graphs on with n1 vertices on one side and n2 vertices on the other side, where n1 is not equal to n2. The claim is that if you have such a graph, complete bipartite graph, with the 2 bipartitions having different number of vertices, then it can never have a Hamiltonian cycle. So if there was a Hamiltonian cycle, how does it look like? I mean, the alternate vertices on that Hamiltonian cycle, once it has a vertex, the next vertex is a B vertex followed by a vertex. Why? Because once you are in a B side, you must go on the A side, right? So now what can you say about such a cycle? Such a cycle must have equal number of vertices from the A and the B side, right? Because such a cycle cannot be, I mean, it doesn't mean that Hamiltonian cycles have to have even length, but in this case when it is a bipartite graph, it must be of even length, right? Because anyway bipartite graphs do not admit any odd cycles, right? And for it to have even number of vertices, it must have equal number of vertices from the A side and the B side. So what we did here is in this case we took a vertex and removed it from the graph, right? We asked, if suppose there is a cut vertex, we are trying to remove it from the graph and we are asking how many components does it create, right? If there is no cut vertex, what will happen? Whatever vertex you remove, you are going to be left with one component. Is that correct? Because by the assumption no vertex is a cut vertex. Right. Similarly, here what we are doing is, suppose there was a bipartite graph which is complete and we have the 2 sides which are unequal in number, then let us look at the smaller side and remove it from the graph. What will you be left with if you remove the smaller side? How does the graph look like, whatever is remaining? Totally disconnected, or it is also called as an independent set. But the independent set or the totally disconnected graph, how many components does it have? Cardinality of the larger set. So what you are saying is, I am removing a set of vertices, and whenever I look at the graph which is remaining, I see the number of components which are larger than the size of this vertex set that I removed. If this happens, then the graph cannot have a Hamiltonian cycle, or we will reverse the condition and say that if G is Hamiltonian, then for every set S belonging to the vertex set, so I'll define this C of G minus S. So what is G minus S? The graph that is obtained after you remove the set S from the original graph, right? So G minus S is another graph which you obtain after you remove S from the graph, and G minus S could be a connected graph, it could be a disconnected graph, it could be made up of multiple components. So C of G minus S counts the number of components that are there in the connected graph, in the graph G minus S, right? So number of connected components is less than or equal to the cardinality of the set S itself, right? And we'll just first stare at this statement, see that we understand this statement and also apply this statement here, right? So what does this say? If the graph has to admits an Hamiltonian cycle, then for every set S of vertices, that is you pick any subset of the vertex set, you remove it from the graph, you will be left with another graph which we are calling as G minus S. We can easily count the number of components of such a graph. We know how to count the number of components. We count that and we compare it with the size of the set S. Then for every such set, we must see that the number of components that we get is less than or equal to the size of the set itself. This is what it says. So if G is Hamiltonian, then for every set this holds. That is all it is saying, right? So let us apply it in the first example. What it is saying is, if you remove one vertex, then the number of components that you get should be less than or equal to 1. That is, if you disconnect the graph, or if you even create two components, you can never hope to have a Hamiltonian cycle. This is what we intuitively agreed, right, to begin with. What does it say here again in the bipartite graph? That if you remove the small, because the smaller set is also a candidate for the set of vertices S here. So if you had removed the smaller side, then it should have left you with the components, the number of components that are less than or equal to the number of the vertices on the side that you removed. But that will not happen because of the asymmetry, and you are removing the smaller side. You cannot hinge the argument on the larger side, because if you remove the larger side, the condition holds, right? But the condition should hold for all the sets S, and in particular the set of vertices on the smaller side is also a candidate set, right? So what does this necessary condition tell us? It doesn't say anything about if you are given a graph, you cannot say whether it is Hamiltonian unless you show a Hamiltonian cycle. But what it allows you to do is, it allows you to prove that the graph is not Hamiltonian, right? Because for proving that a graph is not Hamiltonian, you only need to exhibit one set of vertices whose removal is going to create large enough components, right? So let us revisit our examples. And we agreed that this graph is not Hamiltonian, G1. So can we now show a witness set S? So in fact, let's remove this vertex. If you had removed this vertex, this will be one component, this is another component, this is another component, and this rest of the part is another component. So we have actually 4 components which get created by simply removing one vertex. In fact, this is a cut vertex, right? And that is what exactly this says, that we had already agreed that this graph does not admit a Hamiltonian cycle, but now this is another proof of the same fact. Okay, so now let's go to this second example. Can we now show a witness set which allows us to clearly argue that this necessary condition is violated? Exactly. So now you remove this set X and Y. If you remove this set X and Y, you get A as a single component, B as a single component, and CD as one another component. So you have 3 components that are obtained by removing just 2 vertices, right? So this allows you to prove that this does not admit a Hamiltonian cycle, but we haven't proved that this condition indeed is necessary. That is what we are going to do. And of course, you also see that this condition is not quite efficiently checkable. I mean, does the graph satisfy this condition? If you want to satisfy if you want to check this and say yes, it satisfies this necessary condition, you will have to go over all possible subsets. Right? We haven't said that there is an efficient algorithm, but what we are trying to do is we are trying to take this necessary condition and use it to show that a graph does not admit a Hamiltonian cycle, for which it suffices to simply show one set, which is still efficiently possible. But how do you identify that set? Here we have done it by eyeballing. Okay, so this is what we will prove, that is, if G is Hamiltonian, then for every set S belonging to the vertex set, the number of components of G minus S is less than or equal to the cardinality of S. Okay, so let's do the following. We are under the assumption that we have a Hamiltonian cycle in the graph. So that Hamiltonian cycle is sitting somewhere. We do not necessarily need to know it, but the existence is guaranteed because we are under the condition that if G admits a Hamiltonian cycle. So let us take any set S and remove it from the graph, right? So take any arbitrary set. How do you expect the graph to decompose? It will get decomposed into several components. So we don't know how many, so we will say that there are some k components, right? So we will call these components as C1, C2 up to some Ck, right? And there is also a Hamiltonian cycle. So GVE is Hamiltonian. So let us say that F, which is a subset of the H set, is a Hamiltonian cycle. This is the set S that we have. Okay, good. So how does the Hamiltonian cycle look like with respect to these components that we have? Can we say anything? For example, how many ever vertices are there in this component? It must visit all the vertices in this component. Similarly for any other component, but it need not visit them completely inside the component, right? But if it has to visit them, what are the other? So suppose this vertex this vertex certainly will belong to the Hamiltonian cycle. Now what could be its neighbor in F? F is the cycle. Where could its neighbor reside? There are not too many options, is what I am saying. So where are its choices? Its neighbor can either reside inside this component C1, or it can be in S. It cannot be in C2, right? Because that is not possible, right? So therefore it could be here, or it could be inside the component itself, right? So now there are that is one observation. Similarly, this is true for every component, right? Similarly, let us look at the vertices in S. They are also present on the Hamiltonian cycle. So where are their neighbors in the Hamiltonian cycle? Again, either in S or in any of these C1 to Ck, because S has many options. S connects to everything, and to whom, it actually whatever components it has, it may have a choice to go to any component, right? But there is one cycle which we have, there may be multiple cycles, but one cycle that we have identified, which is F. So let us do a simple counting argument from both sides. So now let me draw these black edges are the edges which are present in the graph itself, right? These are not necessarily the edges of the cycle, and some of the edges of these black edges are going to be cycle edges. So let's say that the cycle may be going like this, it goes like this, it again goes like this, then it comes back, then it traverses for some time inside this, and so on. Correct? So this is how, and then finally it must come back to whatever. So okay, so I hope you agree that this is how the cycle will look like. and the black edges are what we will call as the cut edges, that is they go from S to the components, and the red edges are the cycle edges. If you look at this red edges, the red edges are the edges of F, and with respect to these red edges, every vertex has degree exactly 2 because it is a simple cycle.